Hello everyone, my name is Cameron Hicks, and today I'll be presenting my lab report for Physics 2212, Lab 3, covering series circuits and RC circuits. The goal of this lab was to investigate the behavior of basic circuits. We wanted to put Kirchhoff's loop and junction rules to the test using actual resistors, batteries, and capacitors. Specifically, we measured current and potential differences in a series circuit and then observed the time-dependent behavior of an RC circuit as it charged and discharged. Our experiment is grounded in two major principles. First, the junction rule, which is basically charge conservation, meaning current in equals current out, and the loop rule, or energy conservation, which says the sum of the potential differences around any closed loop has to be zero. We also use Ohm's law, V equals IR, for our resistors, and for the RC circuit, we model the voltage decay as an exponential function where the time constant, tau, is equal to resistance times capacitance. For our model, we assume ideal conditions, zero resistance in the wires and ammeters, and infinite resistance in the voltmeter. For the actual setup, I used two 1.5 volt batteries and a 47 and 100 ohm resistor for the series portion. For the RC circuit, I used a 1 farad capacitor and two different bulbs, one approximately 8 ohms and the one about 20 ohms, to see how the resistance changes with timing. In the series circuit, both ammeters read a steady 6.4 milliamps. My battery measured it at 2.8 volts, and the drops across the resistors were 0.7 and 2 volts respectively. That leaves us with a loop sum about 0.1 volts, which is remarkably close to the theoretical zero. In the RC circuit, the 8 ohm bulb was much faster, charging in about 7.6 seconds, while the 20 ohm bulb took significantly longer, about 51 seconds, showing a clear relationship between resistance and charge time. And this is just a graph reflecting that. When we back calculate the resistance using Ohm's law, we get about 109 ohms for the 47 ohm resistor and 313 ohms for the 100 ohm resistor. These are quite a bit higher than the labeled values, which suggests some significant non-ideal behavior in the components or the meters. However, the RC circuit followed the trend perfectly. High resistance directly led to a larger time constant and slower charging. Comparing the two, the model held up relatively well. The current stayed constant at a 6.4 milliamps throughout the whole circuit, confirming the junction rule. The loop potential summed to nearly zero, confirming the loop rule. And the visual dimming of the bulbs gave us a perfect macro look at the exponential decrease in the current as the capacitor reaches capacity. No experiment is perfect. Our 0.1 volt discrepancy in the loop rule likely comes from the multimeter uncertainty or a tiny bit of resistance in the wires themselves. The internal resistance of the batteries also explains why they read 2.8 volts instead of a perfect 3 volts. Finally, since I was using a manual stopwatch for the bulbs, there's definitely some human reaction time baked into those charging seconds. And also, this could just be faulty equipment. One interesting question is, what if we charge the capacitor with no resistor? In an ideal world where R is zero, the time constant tau would be zero, meaning it would charge instantly. But in real life, it still takes a finite amount of time. Even without a bulb, the wires, the battery's internal chemistry, and even the ammeter have some internal resistance that prevents the instantaneous charge. To wrap up, we successfully verified Kirchhoff's law and observed the characteristic exponential behavior of RC circuits. Despite some non-ideal components, the data clearly supports our theoretical models of energy and charge conservation. Thanks for watching.